Welcome to Texas State University's Chemistry 2330, Introduction to Organic Chemistry. I'm your guide, Dr. David Irvin. We will continue with Chapter 5, Part 2, Reaction Mechanisms of Reactions of Alkenes and Alkynes. Okay, so we looked at the last video and we saw that we had what we called energy diagrams. An energy diagram shows you the energy as the reaction progresses. A reaction mechanism is a step-by-step description of how the reaction actually occurs. It shows you which bonds are breaking and which bonds are forming, the order and relative rates of the different steps. If the reaction takes place in solution, sometimes it describes the role of the solvent. And occasionally we have a catalyst, like an acid catalyst or another catalyst. If we have a catalyst, we'll show you the role of the catalyst. The energy of the entire system during the reaction. Do we go from high energy to low energy? Do we give off heat? Do we absorb heat? And then the reaction mechanism is not just a list of the reagents or the experimental conditions. Okay, that is our reaction formula. Our reaction mechanism is the individual step-by-step of what happens to each and every chemical in that reaction. Okay, so when we develop a reaction mechanism, we actually design experiments to say, okay, what intermediate do I form? Ooh, I don't form an intermediate. That tells me something about that interaction. Okay, and so these ideas are tested again and again. And so that you propose one set of reactions that might account for what happens. And once we start studying that, it might not agree with that. And so we have to come up with new ideas about what happens. If that experiment didn't prove to be correct if that experiment did not support that mechanism, we have to change the mechanism to fit that. Therefore, reaction mechanisms are used to help us discern what they are and how to design better experiments. A reaction mechanism usually uses the symbolism of a curved arrow showing where valence electrons are moving back and forth. Just like when we do loaded stock structures and resonance, the movement of electrons, the forming of bonds and the breaking of bonds is where we see reaction mechanisms give us our most valuable information. Okay, so why do we use mechanisms? One, it helps us give a theoretical framework on how to organize descriptive chemistry, meaning that, okay, we have several things and they all follow the same mechanism, so they must have a similar property to them that allows them to react that way. Oh, we have the same functional group, but it does different things. If that same functional group does different things, maybe it has different mechanisms to go to different products. Okay, it also lets us figure out that, hey, you know, we can predict behavior because if this product does this, this product will do that. And so we can predict behaviors as well. And we use it for a new tool to say, okay, if this compound reacts this way and it should react with this mechanism, I can predict this to be, I can design an experiment and say, hey, does it actually follow this mechanism or not? Or do we have something new? Okay, so there's very, it's mechanisms are not just hocus pocus and, you know, I don't know, I just guess, okay? There's several patterns that happen in mechanisms that we'll see over and over again. For example, when we have an acid catalyst, we'll think, oh, we need to transfer a proton. When we have a hydrogenation reaction, we have to look for what's the catalyst system that we're using. So there's several common themes that we'll see as we go through describing mechanisms. The first pattern is the addition of a proton, okay? In this case, we will have somewhere in the material an acidic proton will be transferred to the more basic system. So in this case here, we'll actually see that in the reaction between acetic acid and ammonia, we have the transfer of these electrons to form a new bond with hydrogen, because we're talking about a Lewis base here. And so it's transferring, it's donating its electrons to grab a hold of this hydrogen, transferring the hydrogen first, giving us a reactive species and another reactive species. So this might be the great first step in a reaction to make something more reactive. Okay, so the next thing we can do is also what we call adding a proton. So instead of moving a proton from one to the other, we can actually take something that already is acidic and transfer it to something else. So in this case here, we could take something like hydronium ion, which is a positively charged species, and we can use the electrons from a double bond to donate to that hydrogen, creating a new sigma bond, a neutral species, and now we have a new reactive intermediate. So transfer of a proton is a very common pattern we'll see in these mechanisms. Okay, so in this case, when we do add this proton, the most accurate way to show the transfer is the idea that the electrons are moving to grab a hold of the proton to generate our new sigma bond on this carbon here, generating our species. Okay, so the electrons from the alkene are reaching out to grab the proton to give us our new covalent bond. Okay, so in pattern 1, we are donating a proton, okay? In pattern 2, we take away a proton. We have something that is basic that is gonna pull away that hydrogen from it. And in this case here, we used the base ammonia to pull away a hydrogen, to give a hydrogen to this base. Now we're gonna use this newly formed Lewis base to take away that proton, okay? So now this is our new base. These electrons will come in, form our new sigma bond with this hydrogen, and these electrons will kick in, giving us our new species here, our neutral species of acetic acid and ammonia, okay? So notice this is just the reverse of pattern 1, where we are taking a proton away from something that is more acidic to form another compound. Excuse me. The third pattern is the reaction of an electrophile and a nucleophile to form a new covalent bond. So let me define electrophile. Electrophile is an electron-poor species that can accept a pair of electrons to form a new covalent bond. Think Lewis acid, okay? They typically have a positive charge or are just electron-poor, okay? A nucleophile tends to be an electron-rich species that can donate a pair. Think Lewis base. Think I already have a pair of electrons that I can donate to form that new covalent bond. So we have the reaction between electrophile, which is positively charged, with a nucleophile, which is negatively charged or partially negatively charged. Okay. The next pattern we have is once we have something, we can do what we call a bond rearrangement, meaning we can move a bond to one adjacent carbon over such that it would make a more stable compound. It only rearranges if it makes a more stable compound, okay? So in these rearrangements, you tend to break a single sigma bond and move it over one atom. You never move it more than one atom, and you only do it to make a more stable compound. And we'll see that time and time again. The other thing we can do is we can break a bond to form a stable molecule or ion, okay? So in the case of this compound here, we actually have a polarized sigma bond, okay? We have carbon and bromine, they have a big electronegativity around, so we have a polarized bond. And what could happen is the bromine, which is more electronegative, will take the electrons with it and leave and dissolve off in solution, leaving us with our new Lewis acid ready to accept protons. Come on, there we go. All right. So with those basic concepts locked, let's talk about different reactions we have with alkenes and alkynes. And I'm going to start with the alkenes to look for patterns we see with that double bond. That pi bond is the reactive species in our alkenes. And so we're going to deal with those electrons first when we do reactions. So the first reaction we're going to do is we're going to call what we call hydrohalogenation, or the addition of hydrogen halides like HCl, HBr, and HI to the double bond, okay? In these reactions, we have the electrons from the double bond reaching out and grabbing a hydrogen, and the bromine ending up to attack the other side of the double bond. So one of the species is going to add to one of the carbons, and the other species is going to add to the other carbon. That's why we call them addition reactions, because they're going to add across that double bond. We can do that same type of addition by with water, and it's called hydration. Typically, it's done with an acid catalyst. And so what we'll end up doing is adding the H to one of the carbons and the OH of water to the other carbon, giving us our new compound with the OH on one carbon and this other hydrogen on this carbon. So again, we're adding across the double bond. Okay, and they're electrophilic additions because that lone pair is electrons out there open in space, and it's easy for them to be reacted with. Okay, and then we can also add halogens to these materials, and it's probably going to undergo a different mechanism because this is a non-polar bond that we have here. But what we'll get is one halogen is going to add to one side of the carbon, one halogen is going to add to the other side of the carbon-carbon double bond to give us our dihalo compound. Okay, so the next reactions we're going to look at is the addition to hydrogen. So we're going to hydrogen halides. Okay, so when we talk about the addition of hydrogen halides across here, it goes into a compound, and we typically use just the materials. We can use them as gases, or we can use them in a solvent that is very polar. It helps to make the reaction happen. Now, when we add HCl across the double bond, we actually have specificity about which side the hydrogen goes on and which side the chlorine goes on, okay? And so this regioselective, meaning that we will selectively add the chlorine to one side versus the other, tells us something about the mechanism. And it gives us repeatable reactions that we can say, okay, this reaction always or most of the time adds in this direction. Okay. In this particular reaction, when we have an alkene that has a substitution on one side and no substitution on the other, and we add an acid halide across it, the halide, or chlorine in this case, will always add to the more substituted side, i.e. the side with more carbon attachments to it. The hydrogen will always add to the side with more hydrogens on it, okay? So this addition reaction, where the hydrogens go where more hydrogens are bonded, is what we call them our Markovnikov's rule, okay? And there's a mechanistic reason we'll describe later about why this happens. But a lot of these reactions have regioselective reactions because of their mechanisms.